Greetings, my fellow geothermal students. It's good to see you here for topic 5 already, and we want to get right into it today. I want to make sure that you've taken a look here at your week 5 of your medium temperature lab. I need to upgrade this to the year 2016. I'll do that this evening. But what's important about this is that you see, hopefully you have your temperature sensors, and you can start your daily data logs. Don't worry if you're not, having your thermometer set already, but do start thinking about that and work towards getting a site. So remember to record your underground temperatures twice daily, at least 8 hours apart. A total of 28 readings, preferably over a 3-week period, starting 9:30. Whoa, 16, right? And we're not going to be done with it by 10/31/16. But we'd like to be having some data by then. So now take a look here at number 1, specific location of underground temperature sensors. Example, capped well casing, 72 inches below surface. A sensor must be protected from air circulation. Or you can drive a post like we talked about before. You can get out there if you've got soft soils, or if your uncle has a backhoe, have him take a couple scoops and then stick a piece of plastic pipe down there and then cap it off. So as long as you're 72 inches below surface, you could use a drainage ditch. You could people have used basement locations or drainage, from road drainage. Type of vegetation is real important. Number 2 here, type of vegetation or shelter building surrounding your surface temperature sensor. The surface sensor must be protected from sunlight. Okay. 3, aspect of your site. Does it face north, south, east, or west? South and west slopes are usually warmer than the northeast slopes as far as surface temperatures go. But that does translate underground somewhat, but not to 6 feet. Oh, I'm giving it away, huh? So 4, slope of site, 0 to 20 degrees. 20 degrees, not percent slope, but 20 degrees in pitch. It's pretty steep. I would say if you can find something below 10 degrees in pitch, you're good. And a way to do that is just to take a protractor and tie a piece of string to a pencil, stick the protractor hole at 0 on the end of your pencil, eyeball down the protractor, and let the string hang straight down, and that'll give you your degree slope. Okay, so medium temperature lab, get you started on that. So a nice resource here, we talked about Google Earth, and hopefully you've downloaded the Google Earth, and so we're going to take a look at that. But also this Iris Earthquake Browser is a real nice piece, and it gives you a little bit more detail in regards to seismology or deliberate earthquakes. You can see that what I've done here is I've selected a region, select new region, or see over here to your left, zoom to region. Let's see what we got. And look right there. 9/25, we had a 2.5 magnitude earthquake from 44 to 111. Yeah, 111 miles down. And what's kind of cool about this is this also includes your transformal boundaries right here. So if we look at this real quick along the edge here, this is that stairway that I was talking about, Gary. Yeah. So we've got the transformal, we've got a subducting oceanic plate that's going underneath, and then now the San Andreas fault is transformal, and this is the San Andreas fault here, this blue. This one doesn't have the reference that I want. So so we're looking for different types of plate boundaries. This is a rift, the Snake River Rift, which is kind of an unusual formation. We've looked at our real-time earthquakes in Google Earth here, and our tectonic plate boundaries. Got the continental convergence, continental rift boundaries, continental transformal, converging, oceanic spreading, oceanic transformal, and subduction zones. So the subduction zone, you see the color here, blue. Well, here's our subduction. Here's our oceanic, Pacific oceanic plate coming in, and it's subducting under the continental plate here. And then you see the red here, the oceanic spreading. You can see what's happening here, and then the green is the transformal. Green, and you see the transformal. And what's important is that you see that these are not always just, this is one great big subduction zone. And if we take a closer look at it, you can actually see where we get rid of this. Now it's covering us up. It actually tells us what our let's do that real quick. The transformal boundaries, or the plate boundaries, are a lot of times hybrid. So we got one big subduction, but then a little further out we've got it mixed together with the oceanic transformal and a subduction zone. So it all comes together up here off of British Columbia. But let's take a look now at that Snake River Rift. Snake River Rift comes in out of Oregon. And it's a continental converging, so the white is what we're looking for. If you're taking your quiz and you say, well, what is a converging plate boundary? Well, we can take a look at the quickest place to go is your Wikipedia. Yeah, so while we're at it here in the Google Earth, quick reference on your tectonic plate boundaries, as well as looking at your Wikipedia. Wikipedia is a great place to come up to speed on that. So if we get into Wikipedia here and we start to look at some different aspects, here's crustal age. This is relatively new. You can actually look and see. Here's your range down here at the bottom. Let's make that a little bit bigger. Millions of years. The whole idea is that you can see that here's where you see the continental United States, South America right here. But this refers to how the oceanic plates are replenished in the center, and how these replenishment zones reflect the shape of the actual continental crusts here. It's kind of like how the Earth is stitched together. And then here we go where it's diving or subducting under the continental plate. So that's that rotary movement. Then you go back to your Google Earth. You can say, okay, what do we have as far as subductive continental plate? There's one right there, huh? Blue. Kind of help you get the answers to your questions in the quizzes. Combination: oceanic converging, oceanic spreading, transformal boundaries, continental transformal boundaries. If you want to say, okay, well, let's get rid of everything except continental transformable boundaries. Oceanic transformal. Let's leave subduction zones in there. Plate convergence. So you see I got rid of those offshore, but then we have the transformal boundary, which is basically what the San Andreas Fault is all about. It's transformal, so there's shear factors associated with the two plates slipping by one another. And we talked about how that exits out into the Gulf of California. Just to help you get the straight A on those quizzes. But you can have a little fun with your Google Earth also. Missoula College, what's that all about? Won't be long for this will be the new Missoula College. See the racetrack over there at the fairgrounds. And soccer fields. Splash, Montana. Nice. But here we are right here. Need to find me. Here's Grizz House 8 right there. On the east side of the dining room. Let's take a quick look now at an earth-coupled geodesic complex here. So here we have one of the projects I'm working on. It's an earth-coupled geodesic complex. These ground level shots are not so hot. But this is all set up such that you vent your hot air out the top of the domes, and you recover your cool air through earth manifolds. So it cools itself in the summer, and then you take that hot air that's generated from your solar thermal and recirculate that, and you use the earth berm, once again, the earth coupling concept, medium temperature, to preheat what comes into your solar panels. So you don't have to, you can gain as much as 60 degrees if you've got a median temperature 42 degrees, which is not uncommon, maybe 48 degrees. It's 20 below zero. By the time the air comes up out of your geothermal earth berm, you're looking at 60 degree temperature gain over outdoor temperature. And you put some sun on that, and brings you right up to 70 some degrees. Put it into radiant slab or some other application. Another one of these geodesic earth coupled complexes. Same idea being that the geodesic dome or dome shape has a third less surface area, so it loses a third less heat. And once again, this is set up such that there's dormers in the top of the dome that create a convective gradient that draws the air, and the only recovery air comes in through white cool tubes that you can barely see here. I'm going to lose it in just a minute. But, so I can make it bigger. Nope. It's as big as it gets, it goes to ground level. But the whole idea being that the air comes out, it gets hot, in solar thermal, it's either vented and then recovered through the earth berm for air conditioning or cooling, or you induce the air into the solar thermal panels along the roof here and here, and along the dome itself, and down along the wall here where the sun arc in the winter is hitting that wall. But the whole idea is that the earth median temperature does a lot to preheat your air in the winter, and the big benefit, the big value, is cooling. And I found that the cooling is one of the major benefits of geothermal earth coupling. Now another great reference for you here is the IRIS Earthquake Browser. So you can Google IRIS Earthquake Browser, install this on your computer. A lot of good information. Right here, once again, you can see the fault lines, the subducting, transformal, the movement patterns here. So this is pulling apart, isn't it? And then we show that blue here indicates transformal. So a little different than what you see in Google Earth. We can take a look at this. Let's go back up here to Montana to see what kind of earthquake we had right here. There we go. On 9/26, 2.7 in Richter scale. Coordinates. Let me see how it's indicated here. 2.6 on the Richter scale. Approximate depth. So it was way down there compared to these other ones. 27th, we had one at 2.4. Let's see, where's that one at? Fifth, 26th. Where's that at? Let's do it. 627. Right here. Ding. The IRIS Earthquake Browser is a real handy tool for you. We're going to be using that to determine our earthquake zones. And here we see this defines the Salmon River Rift. Let's take a closer look at this one here. But let's do it in look out here, the overlay of the whole region. Oops, as close as we get. Let's take a look now at the 3D view of this. It's pretty cool. So we can take a look here where we were at before. And that's epicenter up. Take a look at how deep it is under the surface. North, south, east, and west. The 3D view, once you get zoomed into a specific location, is pretty handy. So let's get that earthquake browser, that IRIS Earthquake Browser, and your Google Earth active on your computers. Okay, let's take a look at the Ring of Fire. We're getting ready for some of that now. So on to our next lecture.